Okay, and there was a question about assignment one. Well, if you start with an empty buffer, so with an empty cache zone, the number of buffer reads should be higher than the number of disk reads. So this is why we insisted on the fact that you have to, for each question, you have to make sure that for that specific query, at least you are using, for that specific table or tables you are using, uh, that the cache should be empty. Because, for instance, if you if you run the same query twice, you can imagine that um, uh, um, all the data that is necessary will sorry. So sometimes the buffer reads is smaller than the number of disk reads. So this should not happen in general. I cannot think of a situation in which that may happen, but I'll look into that. But regardless of whether the cache is empty or not, so regardless of whether the number of disk reads is, for instance, 0 or not, um, the number of buffer reads should be higher than the number of disk reads. But I'll look into that, and you can send me an email about this as well. Okay, there may be something I'm not taking into consideration right now, but in general, this should not happen. Okay. Now, okay, so let's move now to the discussion on concurrency control. And just 1 second, let me also start the recording on Zoom. Okay, so as usual, I'm assuming you can hear me, you can also see me, and you can also see the slides. If this is not the case, just let me know in the chat window. So we are now moving to a new section in the chapter on relational database management systems. So this is, of course, the chapter on traditional database management systems. And we'll talk about database transactions, and we'll talk about, first of all, concurrency control, and then about crash recovery. And we'll see both aspects, concurrency control and crash recovery, rely heavily on this important notion of database transactions. And we will start, and this is, the concurrency control discussion is covered in the COW book 3rd edition by chapters 16 and 17. And we will start first by clarifying what a database transaction means, first rather informally, with an example, a real world example, let's say, just to give you a little idea of what these two sections, concurrency control and then crash recovery, will be about. So we are using, I would say we all use the database transactions every day. For instance, when we do a bank transfer, when we do online shopping, when we book a ride with Uber, when you sign up for a class at HKU, all this most likely relies on database transactions. And let's look now at a concrete example. Let's say you want to buy a ticket to a concert, and of course you will online, of course, and you will start by filling up, let's say, a form with your personal details. Then you put in your credit card number, you click submit. On your phone, you receive a message indicating that the money has been deducted from your account. But then a crash arrives. You see a blue screen, let's say in Windows, and of course, crashes happen for various reasons. They are unavoidable. We cannot be certain when they may or may not occur, but what we can and what we should most make sure about, let's say, is that nothing really bad happens when such a crash arrives, for instance, in the middle of a transaction, in the middle of a ticket purchase operation like the one we saw before. Um, so here, let's say the key message is that changes to a database, for instance, a database for purchasing tickets, should be all or nothing. A database transaction in this concrete example may be a sequence of operations like picking the artist, the date, um, the time, paying with the proper information, and then ultimately getting the ticket. And all this should be should be executed in an all or nothing fashion or atomically. Changes to the database should be all or nothing. We should not have partial executions in which we may deduct the amount from the data from the bank account, but not deliver the ticket, or vice versa. We should not have partial executions in which we deliver the ticket, but we don't deduct, for instance, the corresponding amount from the account of the client. So with a crash, for instance, we may get into trouble if transactions are not all or nothing. We may, for instance, pay without getting the ticket, or vice versa, which of course will be bad for the ticketing company. And in order to avoid such bad outcomes, paying without getting the ticket or vice versa, this will be, let's say, the principle that you should remember for the remaining of our discussion on concurrency control and then crash recovery, that changes to a database should be all or nothing. And this is basically what we will define with transactions. We will see, let's say, formal definitions of transactions, database transactions later on when the moment comes, but you should already get, let's say, the main idea. A transaction, a database transaction, should be a sequence of operation that has to be executed in all or nothing manner. A sequence of changes to a database that must be executed atomically, all or nothing. So since we have discussed a lot, of course, this modular architecture of traditional database management systems, it's reasonable to ask where are transactions handled in this architecture. And I would say it's reasonable to say that from an architectural point of view here, the transaction manager for both concurrency control and crash recovery is somewhat placed, let's say, in parallel with respect to this stack of modules. And in particular, it has, so this is what we could call, let's say, the transaction manager, and it has two subcomponents, modules, one that handles concurrency control and another one that handles crash recovery. And let's say they're in parallel, especially interacting with the modules for the buffer manager, the disk space manager, and the files and index manager. And in particular for the, so this is, we are here, let's say, in our discussion, we'll talk about the transaction manager. And with regards to concurrency control on one hand and crash recovery on the other hand, we will say that it has two corresponding submodules, one for concurrency control, and we'll see that we will often call it the lock manager, and the name for this module will become clear once we continue our discussion today. It will rely on locking mechanisms in particular. And then for crash recovery, the corresponding module will also be called the logging and recovery module, and will clarify why logging is an important aspect. Crash recovery will be done by keeping track of what happens at any given moment in the database in order to allow recovery from crashes. So we are here, let's say, in our discussion, and let's say let's start by clarifying a bit high level the role of these two submodules, the concurrency control manager and the crash recovery manager. And as discussed in the inaugural class, in the first lesson of this course, today any compute service that needs to maintain state is an application on top of some kind of database. State, of course, meaning a database that is changed from one instance to the next, from one state to the next by each. For instance, when you book a ride with Uber, when you buy something on Amazon, when you do a bank transaction, or when you play games online and so on. And in real life, we are not, of course, whenever we use a database, we are not the only ones. We are not alone using that database. Obviously, right now you are doing the practical assignment 1, and in this specific case, you are, of course, the only one using that Oracle server on your laptop and so on. But in general, this is not the case. There are many users that may access the same database, the same data at the same time. Users, of course, sending queries and updates, read requests, let's say, and writing requests, modification requests, many statements that in the end, let's say, boil down to read-write operations on records in a database. And these will be, let's say, the only kind of operations that the database understands in the end, read and write operations on records. And in this setting, there are, let's say, these two crucial roles of a relational database management system: concurrency control and recovery from crashes. So regarding concurrency control, the main goal, the role of the system will be to provide correct and fast data access in the presence of concurrent work by many users. And we will see that this will be done by disorderly processing, disorderly with respect to time, let's say, the processing operations, and yet providing the illusion of order. We'll immediately clarify what this means for concurrency control. And with respect to crash recovery, let's say the role of the system will be to ensure that the database is fault tolerant and not corrupted by any kind of crashes, failures that may arise, whether software, hardware, network failures. And obviously, this is a key aspect in the usage of databases in everyday, let's say, scenarios. You can imagine that, for instance, the database system behind your everyday banking transactions is highly fault tolerant. And the crash recovery module will have to provide storage guarantees for critical data, storage guarantees in particular regarding persistence of results from committed transaction, from results that are successful. The results of such successful transactions should be persistent, should be saved on disk in order to avoid losing them in a situation of a failure, of a crash. And all this, of course, is done on behalf of users in order to help users, programmers, so that they can focus on what they want, for instance, buying a ticket, doing a bank transfer, and so on, instead of spending time and effort on the how are statements executed, especially in the presence of concurrent accesses, especially in the presence of potential crashes, and so on. So all this is done on behalf of users. So let's go deeper now in the discussion on concurrency control. And maybe the first question that we have to clarify is, why bother? More precisely, why do we need to talk about concurrent executions? Why do we need to talk about running queries or read-write transactions on behalf of several users at the same time on the same database? Put otherwise, do we really need to do that? Do we really need to execute concurrently statements from various users on the same data? In other words, why not give access to the database, for instance, only to one user at a time? In this way, of course, removing from the equation, from the discussion altogether, concurrent executions. So why not give access to the database only to one user at a time? And I hope let's say the answer to this question should be straightforward. Unsurprising, the answer is for performance and usability reasons. We cannot afford, the system cannot afford to just give access to one user at a time over the data. And therefore, the system must enable and learn how to handle, let's say, concurrent executions. So for performance reasons, in terms of both throughput and latency, and let's discuss each of them. So remember, throughput means the amount of work or operations that the system can do in a given lapse of time. For instance, we talk about operations per second or transactions per second. TPS is the acronym for that. And obviously, if we want to increase throughput, we need concurrency. By having, for instance, devices that can work in parallel and advance in parallel on different transactions, we can increase throughput. Remember that this idea of parallel execution of operations, for instance, on behalf of different transactions, is valid even for single core machines with no parallelism whatsoever, simply because the disk and the CPU can work in parallel. The disk and the CPU are parallel devices, and therefore, maybe when we do some input-output operations with the disk on behalf of one transaction, we can advance doing some work, some CPU work on another transaction. And in this way, we can increase throughput. Even more obvious, of course, if we have multi-core machines, we can, of course, try to advance in parallel on several transactions, therefore executing them concurrently. Once again, concurrent execution means at the same time, over the same data. And then latency, of course, latency means the delay or the time that is necessary in order to complete a transaction. And so here I would say latency and ultimately usability, because with concurrent execution, multiple transactions that may run at the same time, when we have multiple transactions that run at the same time, with ample resources, one transaction's latency will not be, let's say, impacted or dependent on another unrelated transaction. For instance, if I'm doing a bank transfer, that operation should not be slowed down by another transfer maybe happening at the same time on behalf of another user, another transaction that may be very slow for various reasons. Maybe that other user is taking too much time in order to decide and so on. And so latency is the other performance reason for which we need concurrent executions. In this way, with parallel executions of transactions, one transaction's latency will not be dependent on another unrelated transaction's latency or slowliness, let's say. And both, of course, are important. Throughput and latency are highly important. So this is what we mean by concurrent executions. Let's look at an example here. Concurrent executions of statements or database operations. And that will mean for us interleaving in time, let's say the various steps or stages of different database operations. For instance, when we have here a transaction that transfers money from one account to two other accounts. So 500 units, splitting them among two other accounts. And then at the same time, we have a transaction, the green one here, which corresponds, let's say, to a query that is executed by an analyst in order to compute the global sum over accounts. So we would like to treat each group of instructions as an atomic unit, all or nothing. They should be executed in an all or nothing manner, whether it is the transfer, we should not have a partial transfer of money, whether it is the aggregation of budgets, we should not have a partial aggregation. And so both should be seen as atomic units of work. We don't want partial executions for them. And by concurrent execution of such transactions, such groups of information, we mean that basically their steps may be interleaved in time. We may, for instance, first do this update and then maybe compute part of the sum here, then do this other update on the budget relation, then advance on the aggregation again, and then this other update, and then advance further and maybe finalize the aggregation here. And this is how we will illustrate graphically in our discussion concurrent executions. That is how we will show that this kind of interleaving in time. We'll have a timeline from, let's say, top to bottom, as indicated here, and we'll have transactions, maybe two transactions in general, groups of instructions, once again, that have to be seen as atomic units of work. And here, of course, they're, let's say, happening in parallel. The purple one and the green one, with no indications whatsoever on time. Here we are just displaying them in parallel without necessarily saying which one happens first, which one happens next, and so on. But in general, depending on how we place instructions along this timeline, so higher or lower, we will indicate how instructions are ordered in time. Here, let's say they're just placed in parallel with no indications on time, but we will see that immediately. We'll see such orderings in time on the next slides. And now that this is, let's say, clear, what you should remember from now on is that the database must allow and know how to handle concurrent executions. And at this point, it is important to ask ourselves what could go wrong when we have concurrent executions of transactions, when we have timelines in which we interleave in time the various steps of transactions that may work with the same data. So what could go wrong? And we'll see different types of problems, different kinds of problems that may be due to concurrent execution of transactions. So one thing or one phenomenon that may be due to concurrent executions is the so-called unrepeatable reads. So in order to understand this phenomenon, so remember we have the timeline, and now you can see that, so we have once again two transactions, purple and green, and now by how the operations of the various transactions appear along the timeline, higher or lower, we indicate how they are ordered in time. So here, for instance, this step happens first, then this step, then this step, and then this step. Now, let's understand a bit these two transactions. The green transaction here, so we are using two tables, product and dollar. No, actually, yes, the product and dollar product. So we have, let's say, an inventory of products that cost less than $1, and this is the table dollar product. And then we have another inventory for all the other products. So those with a price, let's say, higher than $1. And so the green transaction reads, let's say, a value, a statistic account from the dollar product table, and then it does the same read a second time. So basically it asks twice how many products we have in the dollar product table. Another application, the purple one, instead updates the same table by doing the following. inserting into the dollar product table some products that may somehow maybe for which the price has been recently reduced and now are less than $1. So all the products from the product table that have a price that is now, let's say recently decreased to be less than $1. And then, of course, such products should, let's say, appear just in one table and not the other. Therefore, they are deleted from the product table. So this is what happens here. So the green transaction just reads the number of products less than $1 twice. For some reason, we need to access this statistic twice, while the purple transaction, following some recent, let's say, decrease in prices for certain products, has to move some products that are now less than $1 from the product table to the dollar product table. And that means inserting them first into the dollar product table and then deleting them from the original table product. Okay, and so what happens here, you can see that in time, we are interleaving, let's say, the steps of these two transactions that, of course, work on the same database and to some extent on the same data, in particular the table dollar product. And so the first application, the green one, reads this count, and then it will, let's say, reread this count, and obviously it will find that the value has been changed because in between these two selects, something happened. Some new products have been inserted into the product table. And this is the so-called, this is the phenomenon that is called unrepeatable reads due to concurrent execution. The same read operation leads to different results because another transaction modified the data in between. And this is a so-called read-write conflict when one transaction is reading and another one is writing on the same data, and this leads to such a situation in which having to read the same statistic twice, we get different results. So this is one first thing that could go wrong, let's say, one potentially problematic phenomenon due to concurrent execution of transactions. And once again, this is how we will graphically represent concurrent executions of transactions, situations, scenarios in which we interleave in time the various steps of transaction by displaying them, let's say here, higher or lower on the timeline. We indicate which one is executed at which step in time, let's say. Okay, now let's look at another thing that could go wrong. And this is the so-called dirty reads phenomenon. Another thing that could go wrong, of course, when we execute transactions concurrently. And this is also a read-write conflict, just as the previous one. So here we have one transaction reading a value that is not yet confirmed by another transaction still in execution. And so more precisely, let's say we are working with an account and the let's say the sum that is present in that account, in a banking account. And let's say the purple application is about is performing some changes. Let's say we are let's say the husband is depositing $100 check to an ATM device and pretends instead of being $100 worth, pretends that this is 1 million worth, as indicated here. Then the ATM, the check deposit system, will analyze the check, for instance, and detect that there is a problem and stop the deposit, abort the deposit operation. This is the abort operation that is indicated here. But what if in between the update and the abort, let's say the wife withdraws 1 million from the ATM that is next door at the same time? If her withdrawal, of course, if let's say the withdrawal application manages, or the withdrawal request manages to see the dirty or the unconfirmed 1 million value, then the bank, of course, would be in trouble. And this is what we call here a dirty read. One transaction, the green one here, reading a value that is not yet confirmed by another transaction that is still in execution. And this, once again, is a phenomenon due to concurrent execution of transactions, interleaving in time of various steps of transactions working over the same data. Dirty read will be a read-write conflict in which one transaction reads a value that is modified but not yet confirmed by another transaction that may, for instance, abort later on. Okay, let's continue and let's see another thing that might go wrong with concurrent executions of transactions. Also here due to a write-read conflict, but illustrating, let's say, a different problem with respect to the previous ones. So another thing that could go wrong is the so-called inconsistent reads. That may, let's say, lead us to conclude that the database is an inconsistent state. So let's look again at the tables we saw before on the inventory of products. And remember, we keep them in two tables: dollar products for products that cost less than $1 and products for all the other products. So those that cost more than $1. And some over the dollar products have just been repriced and may now cost less than $1. And in this case, of course, remember, we must move them from one table to the other. While, of course, after moving them, the total number of products remains the same. And let's say somehow that the total number of products is fixed. There is a constraint, for instance, a rule in the database saying that we have exactly 1,000 products. So in the purple transaction here, we do this moving of products from the product table into the dollar product table in 2 steps. And in between, there are the steps of this green transaction, which simply wants to know how many products we have in total. So for that, it will get, first of all, the count of records from the dollar product, and then the count of records from the product table, and do the sum of the two. And of course, if these two statistics are read in between the operations of the purple transaction, we will get the wrong number, since newly priced products now under $1 will be counted twice because they will appear in both tables. So for the green application, for the green transaction, the constraint, the rule saying that we should have exactly 1,000 products in total will seem to be violated. The data seems to be an inconsistent state with respect to this constraint. Hence the name inconsistent reads. And this is, of course, a phenomenon due to the fact that we have executed in parallel, we have interleaved in time the steps of these two transactions in this specific way. Okay, let's continue. Finally, let's look at the write-write conflict, by which we may have so-called lost updates. So let's say that here we have an application or transaction 1 which writes a new price for a product called Cool Toy by let's say reducing it by shaving off $10.99 from its price. So this of course means several things. First of all, means reading the old price, computing the new price, and then writing the new price. We have another transaction, maybe executed on behalf of another user, which also updates the price for the same product, Cool Toy, by applying, let's say, a 40% decrease. And again, this means reading the old price, computing the new one, and then writing the new price. So we can read, let's say, each SQL update instruction as a sequence of 3 operations. Read mathematical or arithmetic computation, and write. Read, mathematical operation, and write. So we can see each of these update instructions as a sequence of three, let's say, basic operations. Read, mathematical operation, and then write. Looking at this example, let's say that initially the price is 20. Let's try something here. Okay, let's say that initially the price is 20. For this cool toy product. Now, if the two transactions execute their operations without concurrency, let's say first of all T1, then T2, the resulting price, if we execute T1 and then T2, the resulting price will be what exactly? Well, that means, of course, reducing first the price by 10.99 and then reducing it by 40%. And if you do the math, the resulting price would be 5.4. Vice versa, if we execute first transaction 2, so reducing by 40%, and then transaction 1, the resulting price will be 1.01. So first, sorry, if we do transaction 2, then transaction 1. If I'm not mistaken, the result should be 1.01. So we can see here that we have different resulting prices, but both, let's say, possible and acceptable for this scenario when T1 and T2, for instance, arrive at the same time. The requests for updates on the price arrive at the same time. So we should execute them in parallel, and we choose to execute them serially. By the way, this is what we call serial execution of transactions, one transaction at a time. So either T1 then T2 or T2 then T1. Both are, let's say, possible choices for serial executions of these two transactions, leading to different prices. Now, what if the two transactions, both of them, first read the same initial price? So what if we have the following scenario? T1 and T2 read, let's say, one after the other or at the same time, the initial value 20. Let's make this a bit larger. I cannot move it. Sorry. That's not very helpful. Because I cannot see the cursor. Okay, let's continue. So what if T1 and T2 read the initial value, and they read the same value, of course, 20. And they continue, let's say, with their respective computation, and then write the result of that computation. So let's say that T1 reads, then T2 reads, then T1 computes its value, then T2 computes its corresponding value, its corresponding price update. And then T1 writes the new value, and then maybe T2 writes the new value, or vice versa. In any of these scenarios, let me, okay, somehow my Zoom is blocked on that. No. Okay, so let's continue here and we'll see what. So initial value 20 is read by both T1 and T2. Then T1 computes a new value, which is of course 20 minus 10.99, so 9.01. T2 computes its own value, its own update, which is of course a reduction by 40%, so 12. And then T1 writes, let's say 9.01, and then T2 writes, updates the same field in the same record to a new price 12. In that case, of course, we end up with a final value of 12 because the initial write of T1 has been, let's say, replaced, superseded by the write of T2. Or if we invert these two operations, and if T2 writes first and then T1 writes after, we end up with a price of 9.01. So either way, depending on who writes first and who writes second, the price will be either 9.01 or 12. And this is exactly what we will call a race condition, and this is what we'll also call a lost update. The fact that an update from T1, for instance, has been lost because of another update came initially, immediately after from T2 or vice versa. So here, basically seeing 9.01 or 12, this is what we call a race condition. A result, a possible result, having as cause or main cause only the fact that we executed in parallel these two transactions. We executed concurrently these two transactions. So these are, of course, results that we would not obtain without concurrency. If we were, for instance, to execute the transactions serially, one after the other, we saw that serial executions, T1 and then T2, or T2 and then T1, lead to other results. The price may be 5.4 or maybe 0.1.01. So these are, let's say, acceptable outcomes after executing T1 and T2. However, outcomes or results such as 9.01 or 12 are simply due to the fact that we executed in parallel concurrently these two transactions. And we had in the process lost updates. So this is what we'll call lost updates and race conditions, possible results having as cause, as only cause, let's say, the concurrent execution of transactions. Okay, now let's see if I can continue, and I cannot, as I was afraid it may happen. One second, we will figure it out. No. Okay. Now, okay. All we have to do is restart the sharing. Good. Sorry about this problem. Okay, so what we have seen so far are, let's say, possible problems due to concurrent executions of transactions. What might go wrong when we execute in parallel various transactions working on the same data. And now that we have talked about that, what could go wrong with concurrent executions of transactions, let's clarify more formally what database transactions are in fact, because for now, of course, we just use, let's say, an informal definition for them, one that we got through the initial example. So let's start first of all with their role or their importance, and we can undoubtedly say that database transactions represent a major component of relational database management systems. They're critical to most, if not all, applications using databases. We could not go for a day without database transactions, whether it is for banking, shopping, transport, you name the domain, basically, they all need database transactions. And to illustrate their importance, among the database researchers who received the highest distinction in computer science, which is the Turing Award, we have, for instance, Jim Gray, who received this award for inventing transaction processing in the 80s, long ago, let's say, well, end of the 70s rather, and for that he received, for his contributions in the area of transaction processing, he received this distinction in 1998. And you have here, of course, other recipients of this important prize for their contributions in the area of database research. So what is a transaction? Well, simply put, it's a collection of operations that, let's say, together form a single logical unit of work, an atomic unit of work. Atomic in the sense that a transaction must be executed all or nothing. From the application's perspective, a transaction starts with an indication, a begin transaction command, begin transaction statement, and then is made up of a sequence of SQL statements for selection or for update of data, and then end with another statement indicating that this is the end of the transaction. For instance, example, maybe transfer of money between accounts, booking a package including a flight, a hotel, and then a car together on Expedia and so on. Now, from the database perspective, a transaction is a bit different or much simpler in a way. It will simply be a sequence of read and write operations over database objects, for instance, records in a table. And so this perspective of just reads and writes of records ignores completely, let's say, the program logic. The fact that at a higher level, we are doing, for instance, a bank transfer, or we are booking a trip. And any computation, in fact, may be done on the, maybe performed on the data, and yet from the database perspective, the transaction will simply be a sequence of reads and writes. And the program logic will be invisible, let's say, to the database management system. Now, we also have to say that this separation, how applications see transactions and how the transaction manager in particular sees transactions, this is somehow somewhat to a certain degree, let's say, is reconsidered in some modern systems. But for our discussion, we'll continue with this assumption that the program logic is basically invisible to the transaction manager, to the database management system. The transaction manager will simply see a transaction as a sequence of reads and writes, ignoring, not being able to understand that we are doing a bank transfer, we are booking a trip on Expedia and so on. So here is a transaction from the transaction manager's perspective, corresponding, for instance, to a bank transfer. It will have a start. It will read the amount of data from the account R. It will remove 100 units. It will write the new value in the account R. R may be a record in a table. It will read the value for the destination account, add 100 to it, and then write it. And that's the end of the transaction. So this is, once again, the database perspective or the transaction manager perspective on transactions where, let's say, the program logic, for instance, the fact that here we are doing a bank transfer is ignored. Okay, and with respect to database transactions, a relational database management system must ensure 4 important guarantees, the ACID guarantees that we have already mentioned in the inaugural class. Atomicity, all actions in a transaction happen or none happens. So basically no partial executions of transactions. Consistency, if the database starts out consistent or if a transaction takes the database in a consistent state, it should also leave it at the end of the transaction in a consistent state. Isolation basically means that the execution of each transaction should be isolated from that of other transactions. We could also rephrase that as no race conditions. And remember, in our example on repricing the same product, the race condition was the situation in which we ended up with a price that was only the consequence of executing in parallel the 2 transactions, a price that we would not get if transactions were to be executed one at a time, right? Remember T1 and T2 that were modifying the price over the same product. So isolation basically means no race condition. And that, of course, means transactions execute as if they are isolated, let's say, from the effects or the side effects of other transactions being executed at the same time concurrently over the same data. And durability, if a transaction commits, its effects must be permanent, must be persistent, and that, of course, means saved to disk. So regarding atomicity and durability, these are handled by the crash recovery manager, and we will talk about them in more detail next time. So let's say we have to keep in mind that transactions can end in 2 ways, successfully with a commit and unsuccessfully with an abort. That may be due, for instance, to a system crash. And there may be many reasons for aborting, for ending a transaction unsuccessfully. For instance, the user may change his or her mind and hits Control C, for instance, during the execution of the transaction. Or there may be a system crash and so on. And with respect to committing or aborting transactions, the system must ensure atomicity, no partial executions, and durability. If a transaction ended successfully with a commit, then its effects must be persistent, must be durable. And we will see next time, next week, that the database management system does ensures atomicity and durability by doing a lot of work in terms of logging actions and undoing them in the case of aborted transactions, or maybe redoing them in the case of a crash in order to make sure that successful transactions are durable. The effects of successful transactions are persistent. So we'll talk more about how the system enforces atomicity and durability next time. And in particular, we will see the logging mechanisms that are necessary for that. So here is an example for atomicity and durability. So we have our transaction that transfers money from one account to another. And if this transaction fails after step 4, so after money has been removed from the initial account and before step 7, of course, money will be lost and we'll have an inconsistent database. And the role of the DBMS should be to ensure that effects, updates of such partially executed transactions will always be cancelled. Cannot be made, let's say, permanent. And durability, for instance, if after doing such a bank transfer, the user is notified that the transaction is complete, then this should be the final word on this. He should or she should rest at ease that the 100 units have been transferred between the two accounts. This should be the final word on it. And even if a crash comes immediately after this notification, immediately after the transaction has completed successfully, then this should have no effect on the result of this transaction. Okay, now regarding consistency. So consistency is about preservation with respect to integrity constraints. And so given a consistent database state after the execution of a transaction, we should also end up in a consistent database state. Integrity constraints are usually specified by users when we create a table or later on. For instance, we may say that the total number of products from the two tables we saw before should be equal to 1,000. That's an assertion that can be specified by the user. And then transactions, it will be the role of the database management system to check that any transaction that takes the database in a consistent state, where, for instance, we have exactly 1,000 products, also leaves the database in a consistent state with the same number of products. Any transaction that may violate such an integrity constraints will be aborted by the system. The system will intervene in order to cancel such transactions that leave the database in an inconsistent state. So this is the role of the database management system here with respect to consistency. It will automatically check that a transaction will leave any transaction will leave the database in a consistent state, and whenever this is not the case, the transaction will be aborted. Okay, and now regarding isolation, and I would say the most important guarantee with respect to today's discussion. When the database management system will interleave in time, will mix in time the execution of many transactions, it will do so not in any possible way, in arbitrary ways, but it will do so by making sure that these executions in parallel of transactions do not interfere, let's say, with one another. And ultimately, that the result will be as if each transaction executes as if it is run by itself. It is the only one being executed over the data. So in other words, the database system must ensure that there are no race conditions. And remember that we saw such an example before, race conditions being results of concurrent executions that we would not get if transactions were to be executed one at a time instead of in parallel. So results that would not be possible without concurrency. So let's clarify a bit more what means without concurrency. Remember, this means transactions are not executed in parallel, but are executed one after the other, serially, right? And this is what we'll call serial execution of transaction, one transaction at a time entirely, and so one transaction after the other. Now, obviously, isolation can be easily achieved precisely by serial executions. But we also said that this is not really interesting because of performance. We cannot afford to execute just one transaction at a time. For throughput and latency, we must accept that transactions should be executed in parallel instead of serially. And so the database management system must find better ways, better ideas than serial execution in order to ensure isolation and in order to avoid race conditions like the ones we saw before on the price being modified twice. And so obviously we need clear definitions for what no race conditions may mean. What does it mean to ensure isolation? What does it mean to ensure that there are no race conditions? And we will see that bottom line will be that no race conditions for us means that the net effect, let's say, of concurrent executions of transactions should be identical to executing the transactions in some serial order. And here, some is a very important word. There may be many possible serial orders, and it's sufficient, let's say, to have an end result that is equivalent, is the same as some one of the possible serial executions of transactions. And so here, any serial order will do, let's say. Any serial order will be okay to define what is not a race condition. Remember that with two transactions, T1 and T2 modifying the same price, we could end up with, if I remember correctly, with, I don't have it anymore, but with two different prices, but they were both acceptable, right? Both possible prices that we would get if transactions were to be executed one after the other. So, and this is exactly what we will use, let's say, in order to define what no race conditions means. Executing in parallel transactions in such a way that the final result is the same, is equivalent to one, is equivalent to the result that we would get by some one possible serial execution of transactions. So obviously here there is, let's say, a mismatch of perspective that makes, let's say, the job of the database management system even harder or more important. We as users, we think about our transactions in isolation, right? We just have our transaction in mind and we don't necessarily have a clear view over what others may be doing with the same data. While, of course, the database management system must see the big picture and must consider the effects of other concurrent transactions. Okay, so let's look at an example about this notion of isolation and the fact that we want to ensure there are no race conditions. So here we have two transactions working over the same data. So the first one does a bank transfer, is the one that we saw before, while the other one just reads, oh, there's something missing here, reads R and S and just computes the sum of the two. Okay, now if we execute them in parallel in this order, and remember the timeline is going from top to bottom, and that means we first execute operations 1, 2, and 3 and 4 of T1, then we execute operations 1, 2, 3, 4 of T2, and only after that we execute operations 5, 6, 7, 8 of T1. If we pick this schedule, and by the way, this is what we'll call a schedule in the context of concurrent executions of transactions. If the system picks this schedule, well, what will happen? We will have a so-called race condition. Why? Well, if we execute entirely T1 and then we execute entirely T2, obviously, let's say initially we have 1,000 units in each account. If we first execute the bank transfer and then we execute the read that sums the two accounts, at the end, let's say T2 will read the value 2000, which is the same value that T2 would see if we were to execute the transactions serially in the opposite order, first T2 and then T1. So here, obviously, we have two possible serial executions, T1, then T2, or vice versa, T2, then T1. And in both of them, by both serial executions, the statistic, let's say R plus S, will be the same, 2000. Both serial executions will lead to the same value. However, if we have a concurrent execution in which the steps of these two transactions are mixed in time in this specific way, illustrated here, then of course, since we first remove 100 from one account, then we do the sum of the two accounts. Here we will see a value of 900 plus 1000, so 1900, which is of course a result that we see. It's the effect of simply the effect of the concurrent execution of these two transactions. It's a result that we would not see without concurrency, and this is what we call a race condition. This is what we want to avoid, what we want to guarantee by this property of isolation. So here, once again, if we execute these operations interleaved in time, ordered in time as indicated here, and so remember higher means earlier, then T2 will print an amount basically that is short of 100. This is what we call a race condition, an effect that is due only to, let's say, a wrong or bad concurrent execution of these two transactions. Okay, so hoping that this is clear, let's look at this quick quiz. Let's link the items to the two lists, and I think we have already done this before, so I will do it directly. Obviously, atomicity means all or nothing. Consistency means maintaining integrity constraints. Isolation means no race conditions. And durability means committed data survives any crashes, failures that may come immediately, let's say, after the commit, the successful ending of a transaction. Okay, so as a summary and also as a plan ahead, I would say, so ACID transactions make guarantees that improve performance on one hand via concurrency, and also relieve help programmers of all kinds of correctness concerns we may have. Basically, all the details pertaining to concurrency and failures are hidden, are happening, let's say, behind the curtains, and we as users and programmers, we do not have to worry about them. And there are two key issues to consider and two mechanisms that we'll have to clarify together. For concurrency control, we'll see how this is done, is enforced, in order to make sure that there are no race conditions via locking mechanisms and let's say protocols such as two-phase locking. And then for recovery, we will see how this is handled and how atomicity and durability are enforced via logging mechanisms, and in particular protocols such as the write-ahead logging that we'll talk about next week. Okay, so let's start now the discussion on concurrency control. And remember, there is, let's say, the easy way and the hard way for dealing with concurrency and providing isolation. The easy way, of course, is means one transaction at a time, so serial execution of a bunch of transactions. But we have already said that this is great, this is safe, but slow. We cannot realistically consider this. Is simply slow, and I would say it will render the system unusable in any realistic scenario. And so we must interleave in time operations on behalf of various transactions for performance, for both throughput and latency. And now, of course, the question that remains to be clarified is how do we, even if we interleave in time operations of various transactions, how do we ensure correctness? How do we ensure that nothing bad happens? How do we ensure that there are no race conditions, no results, no final, let's say, effects of executions that are only due to the fact that we executed in parallel transactions, that we executed concurrently transactions. And so in order to make sure that nothing bad happens, that we only, the system only picks, let's say, correct concurrent executions of transactions, obviously we need a definition of correctness, a definition of correctness for schedules of that will mix in time, will interleave in time operations of various transactions. And so this is what we'll define next. So first of all, we'll define, so for us, let's say a schedule is simply an ordering with respect to time, of course, of operations from various transactions that are to be executed. And ordering in time, let's say one operation at each clock tick somehow. We'll see an example of that on the next slide. And so with this, let's say, as the definition of schedules, a serial schedule will be one in which we have basically one transaction at a time. So each transaction runs from start to finish without any interfering actions from other transactions. So we, for instance, if we have T1 and T2, in a serial schedule, we may have all the operations of T1, then all the operations of T2, or vice versa, all the operations of T1, then all the operations of T2, then all the operations of T1. So this is what a serial schedule means. And for instance, for two concurrent transactions, we have two possible serial schedules. Now, we'll also define what equivalent schedules mean. And this is a necessary definition in order to define after that correctness. And so two schedules will be equivalent if they involve the same transactions and the same operations. They do the same thing, but maybe in different orders, let's say. And each individual transaction's actions are ordered in the same or the right way. And this is an obvious condition here. If we have transaction 1 with operations 1, 2, and 3, then in any schedule, they should appear ordered in time in this way. First, step 1 of transaction 1, and then at some point, step 2 of that transaction, and then at some point, step 3 of that same transaction. We'll not reorder the steps of the same transaction. We will not first do step 3 of transaction 1, and only after that, step 1 of transaction 1, and so on. So for each individual transaction, their actions are always ordered in the same or the right way. There is only one possible way, let's say. And both schedules leave the database in the same final state. So basically, two schedules are equivalent if they do the same work, but maybe in a different way of interleaving the operations of the transactions, but they lead to the same final state or the same final result of the database. And that being said, we'll say that a schedule is serializable if it is equivalent to any serial schedule. So you know what serial schedule means, one transaction at a time. And our notion of correctness for now will be serializable. We will accept any schedule that even if mixing in time operations from the various transactions leads to a result that is the same as the result of a serial schedule. So a schedule for us will be correct, will be serializable if it is equivalent to some serial schedule, to any serial schedule that is possible. Remember, for instance, that with two transactions, we just have two ways of ordering them in a serial schedule, T1, then T2, or vice versa, T2, then T1. And in such a situation, a serializable schedule will be one that leads to the same result as the serial schedule T1 then T2, or leads to the same result as the serial schedule T2 then T1. Okay, so let's look at an example for that. So we have here, of course, a schedule that is serial, right? So we have T1 that transfers 100 from account A to account B. We have T2 that adds 10% to both A and B. Okay, let's say that initially A and B are 200 before all this happens. And we have a serial schedule in which we first do T1 entirely and then we do T2 entirely. What will be the final state of the database? What will be the final value of A and B after this schedule that is once again a serial one? What do you think? What will be the value of A, initially 200, after taking 100 out of it and then adding 10%? Of course, 110. And the same for B, we add 100, so 300 plus 10%, so 330. Right. So that's the result, the state of the database after this serial schedule of these two transactions. Let's look at another serial schedule, the only other possible serial schedule in which we first do T2 and then we do T1. Starting from the same initial values, what will now be the state of the database? What will now be the value for A and for B after executing T2 and then T1? Exactly, 120 and 320. Very good. So what we can see already from this example is that different serial schedules may lead to different final states or different results, different end results of the database. And we consider or we see both of these serial schedules as possible or correct or acceptable. Both are, let's say, valid for comparison in our definition of serializability. Okay, so if we have a schedule that leads to 110 and then 300 and 330, or if it leads to 120 and 320, that's fine. These are, let's say, the acceptable results of any non-serial execution of transactions. So let's look at such a schedule now, which is not a serial one, and we can see that it mixes in time, it interleaves in time the operations of the two transactions. First, these four operations from T1, then these four operations from T2, then this part from T1, and then finally this part from T2. Let's say that once again, initially we have 200 as our starting values. What will be the value of A and B? What will be the state of the database after executing this schedule, after executing these transactions in this specific order? 110 and 330 indeed. This will be the state of the database after this schedule. So what we can see here obviously is that we have a schedule that is not serial, a non-serial schedule, but one that leads to the same result as schedule 1, which was serial. So we have a schedule here that is equivalent to schedule 1, leads to the same result. This is what equivalence means for us. Once, of course, we accept that we are talking about the same operations ordered in the same way within each transaction. So we have a schedule that is not serial, but is equivalent to schedule 1. And this is what we mean serializable. And that will be ultimately the role of the transaction manager, also called the scheduler, since it will reason about schedules, possible ways of interleaving in time operations of transactions. Its role will be to find such schedules, such correct schedules. Correctness for us, meaning for now, serializability. A correct schedule will be one that is serializable, that leads to the same result as any serial schedule. Okay, now hoping that this is understood, we know, let's say, what the scheduler, the transaction manager, needs to look for. But this is not, let's say, the final word on it, because our current definition of correctness, of correct schedules or good schedules, is of course intuitive but hard to enforce, hard to check. How can we check that the schedule is serializable? Well, obviously for that we should we should get the state of the database after each possible serial execution. And obviously there may be many serial executions. With just 2 transactions, it's easy. We just have 2 possible serial executions. But what if we have 2,000 transactions? In that case, of course, we have an exponential number in the number of transactions, a number of serial executions that is exponential in the number of transactions. So we'll have an exponent of 2,000, so way too much possible serial executions that we need to take into account. So this definition for correctness, serializability, is easy to formulate and intuitive, but definitely not easy to check, not easy to enforce, because there may be too many possible serial executions and results of serial executions we need to think about, we need to compute. And so we need instead a different or much simpler definition of correctness, one that only looks, let's say, at a candidate schedule, like schedule 3 before, and is able to label it, let's say, as good or bad, or acceptable or not acceptable, correct or incorrect. And this is what we will, let's say, build one step at a time next. Of course, continuing the discussion next week, we'll see an alternative definition of correctness for schedules that is much easier to enforce than serializability. And for that, we will use the notion of conflicting operations. We say that two operations are conflicting if they are done by different transactions. One is from transaction 1, the other one from transaction 2. They're on the same object, let's say the same record, and at least one of them is a write. So if we have 2 operations that just read the same data, they're not conflicting. But otherwise, if one of them writes, modifies that data, then they are conflicting. And with that in mind, with this notion of conflicting operations, we can now define a lighter, easier notion of correctness for schedules that we'll call conflict serializability. So we will again define it in 2 steps. We'll say that 2 schedules are conflict equivalent if and only if they involve the same actions of the same transactions, and every pair of conflicting actions is ordered in the same way. For instance, first action 1, then action 2, or vice versa. And we'll say that a schedule is conflict serializable if it is conflict equivalent to some serial schedule. So what changed with respect to the previous definition of correctness or acceptable schedules? Instead of just equivalent, result equivalent to some serial schedule, now we replace that by conflict equivalence, what we have just defined here. So an acceptable schedule for us now will be one that is conflict equivalent to some serial schedule. And first of all, obviously this is a different notion, a different definition of acceptable schedules than what we had before, and there may be good serializable schedules that are not conflict serializable. So I would say this should not come as a surprise. There is no free lunch, let's say here. We get a correctness definition that we will see is much easier to check, but we also lose something. We lose some potentially interesting or valid schedules that are serializable, but are not conflict serializable. Okay, so let's see an example on conflict serializability, and we will finalize the discussion on that for today. And this will also give us, let's say, the intuition behind this new definition of correctness. And this intuition is provided, let's say, also as an alternative definition for conflict serializability, which goes as follows. A schedule is conflict serializable if we are able to transform that schedule into a serial one by simply swapping consecutive non-conflicting operations of different transactions. So swapping in time, of course, consecutive non-conflicting operations of different transactions. And so this is, in a way, an alternative definition that is for conflict serializability that is operational. You can imagine we can make a testing algorithm out of that. We look at the schedule and we have an algorithm asking, can we transform it into a serial one by simply swapping at each step some two consecutive non-conflicting operations of different transactions. And so we can imagine a simple algorithm that would test conflict serializability simply by looking to swap such operations. So you have here such a schedule, and let's ask ourselves, is it conflict serializable? And we make this question more precise by asking ourselves, can we transform it into a serial one just by swapping at each step consecutive non-conflicting operations of different transactions? So what do you think? Let's see. So this is what we start with. For instance, this is what just happened. Can we swap? Let me take the pointer. Can we swap these two operations? They're obviously consecutive in time. One comes after the other. By the way, here the timeline goes left to right. I forgot to mention that. So they're consecutive. They're not conflicting. Why? Because they work on different records. A and B, let's say, are records. And so we can definitely swap them. Okay, let's continue. These two, we can also swap them because they are also working on different records. They are both writes, but they're not conflicting because they work on different records. So we can swap them. Let's continue. What about these two? Can we swap them? Of course, because they're working on different records and they're both reads anyway. So even if they were on the same record, they would not be conflicting. What about these two? We can also swap them because one of them is a write, one of them is a read, but they are on different records. So they are not conflicting. We can swap them, and we just ended up with a serial schedule, one that executes the actions of the top transaction. So by the way, the top line was one transaction, the second line was another transaction. And now basically we do all of T1 and then we do all of T2. So this is what we mean, what we call conflict serializability. For instance, this example you can see that there's no way to swap consecutive non-conflicting operations in order to end up with a serial schedule. Okay, so let's to further understand conflict serializability, we will see another way of checking that a schedule is conflict serializable that does not work with this notion of consecutive non-conflicting operations that are to be swapped, but works with a so-called dependency graph instead. But we will continue the discussion next week about that. And so next week we will finalize, of course, the discussion on concurrency control, and then we will also continue with the discussion on crash recovery. Okay, so this is all for today. A few remarks on the practical assignment one as well. You should have received the message that we have postponed the deadline for this assignment by 1 week. But you should not wait longer. You should really start working. If it's not already the case, you should start working on this assignment, and more importantly, make sure that you have the necessary environment in order to complete this assignment. If you encounter any problems, do not hesitate to send us an email, to send us a question via the forum, most of all. And if we cannot help you directly by answering your questions in the forum, do not hesitate either to contact the TAs, maybe to schedule a face-to-face meeting in order for them to help you with the starting steps, basically to have the necessary environment in order to complete the work. Okay, so this is all for today. See you next week. Thank you all for attending. And of course, I will at 6 p.m. I will be in the office hours Zoom meeting, which has also changed. I just sent a news notification about that, so you should, if you want to attend this meeting, check the new link for that. So 6 to 6:30 p.m. of course. Okay, thank you all and see you next week. Bye bye.